This video, I'm just continuing on with the circular motion questions for grade 9 ASP, end of term 2 focus questions. And this question over here is talking about the centripetal acceleration and how does it impact the direction of an object moving. So the centripetal acceleration is basically center seeking, pointing towards the center no matter what. So for this reason, this object will begin to keep turning. It's going to keep turning towards the center. If it's a car, a yo-yo, if it's a satellite around Earth, the centripetal acceleration will keep it coming towards the center, which means the direction is always changing. It is not a straight line. That was the tangential speed, so that is wrong. It makes it continuously change directions. I like it. It doesn't slow it down, and obviously it does have an effect. It changes the direction. The speed doesn't need to change. It can be a constant speed, but the direction is changing. So that means it is accelerating. Accelerating is a change of direction or a change of speed, as you may remember. So direction changes, it is accelerating. And I've given away the answer for question 4 now. It points to the center of the circle. So it points to the center of the circle. What force acts as a centripetal force in a swinging pendulum? A pendulum, that is the little bob at the end of a rope, and it swings up that way and it goes around, swings the other way, it goes back and forward. So something like this. This is a pendulum, and the thing that makes it swing is of course the actual rope or the string itself. There is tension. This is the force keeping it. Without this tension, if I cut this, this will just keep going off in a straight line. So the thing that's keeping this in the air is the tension in the string. Gravity pulls down, fine, gravity does pull down, but that's not the thing keeping it in a circular motion. If this was to keep going, it would end up, if I swing it around, it will end up in a circular motion because of this string. In case you don't know what a pendulum is, pendulum, I've spelled it wrong, but it's fine. That's a pendulum there, this thing. It swings back and forward, like this. That's a pendulum. Very nice. Okay, let's continue. Next, we have a yo-yo swirling around in a circle. It's just like this. In what direction must a force act on the yo-yo? So we're again talking about this centripetal, which is going towards the center of the circle. So you will say towards the center, towards the center. Okay. Next, we have what exerts the force. Again, this is a yo-yo. It's on a string. This is attached by a string. This is the force that's keeping it. So I will say the tension. Tension in this string. Tension. If this was, let's say, gravity, if you wanted to pick gravity, that means you'd have like a planet here and moon. The moon is going around and it is being held in place by our gravity. So that would be another example of this force. But right now, tension in the string. If you let go of the string of the yo-yo, what direction would they travel? So in this case, according to Newton's law, it will continue to move in a straight line. So it will continue to move in a straight line. I will type it out. It's probably easier to do that. It will continue to move in a straight line. Okay, so this is of course Newton's first law. Newton's first law states it will move at a constant speed unless there's a force acting on it. So without the force of the yo-yo, it will keep going in a straight line and it will not stop. Okay, so if it's something throwing in the air, you could say that, oh, well, there's gravity acting on it and that's going to make it accelerate and slow down. You can mention that too. You could say that it will accelerate to the ground or the floor due to gravity. And that's Newton's second law, right? F equals ma is Newton's second law. That's two different answers you could give depending on the scenario or situation. And this, obviously, it does get let go, it does move, and it will be like a projectile in that case. It will start to fall, just like the previous video, projectile motion. It will hit the ground. So something along those lines is fine. Okay, let's go. Next, we need to find the speed at the spinning of this with this tension. Very nice. So there's a formula associated with it, of course. We have a rule, F equals ma. We know F equals ma, by the way, so that's a general formula. And I know A from circular motion is v squared over r. What we can do, because we don't have A, I can just combine these two. I will do F equals m, and I will write not A, I will write v squared over r. V squared over r. Why am I doing this? Well, I have the force, that's 12 newtons. This time I'll use the shift solve method. You can actually use just rearranging the formula, but let's try another way. Mass, I have it. There's my mass there, kilograms. That's very good, 0.75. I like it. Multiplied by, I need the speed, so that'll be v squared divided by the what? Divided by the radius. That's supposed to be an r. The radius is the string itself, or whatever this is. This is a string, yes. This is the radius. So that'll be 1.5. So going ahead and solving this, if you were to do shift solve here, because the v is squared, it might lag a little, but don't be afraid. You will get your answer. If you solve that, you should hopefully get 4.9 for the speed. Next, we're trying to find the centripetal acceleration of the hammer. So the general formula is A is v squared over r. Small problem here, we have a mass, we have this, we don't seem to have the speed. So we need to go and find it. As you know, speed is distance over time. And in circular motion, the distance, one complete revolution, this is 2 pi, right? 2 pi r over time. That's how you find the distance around a circle. That's what we did in class. So to find that, we will do 2 pi r. And the time, we have 1 second, so that's easy. So I will just write 2 pi, multiply that by my radius. What is my radius? I have it somewhere, 1.8. 1.8, and I'm going to divide that by 1. That doesn't really make a difference either way. 2 times pi times 1.8, and if I was to do that, I will get 11.3 meters per second. Perfect. I can now use it in here. So I'm going to take this, I'm going to bring it over here now. V squared, I have the V. 11.3 squared divided by my radius again, so I'm just cancelling the r's, but it doesn't matter. I'll just do it one at a time. There we go. Nice and easy. And I'm going to do that answer squared, and I'm going to divide that by 1.8. I should get 71 meters per second squared. That's the unit for acceleration, meters per second squared. You get 1 mark for the unit, please don't forget. Next, we'll find the tension in the cable. The tension is the force, so I could do MA. That will be my tension. I have the M, it is 7 kgs, multiplied by 71. 7 times 71, stick that into your calculator. Hopefully, you will get roughly 500 odd newtons. That's it rounded. Otherwise, obviously, 7 times 71, you're going to get 497. I've just rounded it to 500. There we go, nice and easy. So let's move on. Here we go. We are now moving up this slope this way. Work done is usually, W is normally the formula. I can see that this is a work question. For FD cos theta, usually. If there is an angle, we will use it. Now, you might think of this question, oh, we have an angle, we're going to use 30 degrees. You would be wrong for this. Why would you be wrong? Let's find out. Here is the force. It is moving that way. It is moving in the direction of the force. There is no angle between the force and the direction of movement. So there is no angle between them. That means I will not need to include cos theta. This will become cos of 0, which is 1. If you put that in your calculator, cos of 0, you will get 1. There is no need. But what we do need is to find this distance right here. We need to figure out that distance. So we don't have it. So I need to go back to my friend math and ask, how can we do it? We have an angle. This is the opposite. This is the hypotenuse. And this is my adjacent. I have my opposite. I need the hypotenuse. I have an angle, O and H. Back to the previous video. So, that's sine. S-O-H. This is SOHCAHTOA, right? We're going to use the sine. I need to find the hypotenuse. What does that mean? Let's do it. Sine of the angle is O over H. I need H. I will rearrange the formula. You can shift solve if you like. I will rearrange, swapping this around. I will have h, that's a h, it's a terrible h, equals opposite over sine of the angle. Fine. What is my opposite? I have 3 divided by sine 30. Sine 30 is 0.5, so divided by half, that'll give me 6, basically. You can check with your calculator, why not? Let's just check, 3 divided by sine 30. You should get 6, very good. This is my distance, meters. That is the distance he's moving in. I'm not going to use 3 in my formula because that's the height. I am moving along this distance, that's the point of a ramp. You will be able to move a longer distance and require less force to do it. The work will be the same, but anyway. The longer distance that we have just figured out is 6 meters. The force we have applied is 100. 100, multiply that by 6, 100 times 6, and you will get your answer of 600 joules. Very nice. Now, the work done according to this question, we need to do it. And now, look, this will move to the right. My force is applied at an angle. Now there is an angle between my force and my movement. It is positive. It is in the same direction. I just need to find the horizontal component. And if you remember, a horizontal component is h cos theta. So that's fine. I can directly just put that into our formula. W equals fd cos theta. I can just do that and I will get the answer straight away. I don't need to do 2 steps. I can do it in one go. Force is 200. It's actually supposed to be 200 cos 45, but I can add the cos 45 at the end. It doesn't make a difference. 200 multiplied by the distance. We have the distance of 5 meters. And I'm going to multiply that by cos 45. That is the formula. Nicely done. Putting that into our calculator, you should get an answer that's approximately 710. I will pick B in this case. Very nice. To move a suitcase up to the check-in and stand, it pushes with a horizontal force through a distance of this. If the work done is this, what is the force? So no angle in this case, so I don't need to do it. W equals Fd. This time I'm asked for force. I'll rearrange. I'll divide both sides by D. So I'll have F equals W divided by D. W divided by D, fine. 32 divided by 0.95. 32 divided by 0.95, I will get roughly 34 newtons. And don't forget the unit for force, newtons. Unit for work, joules. And you can actually check your units just by looking at previous questions. This one says, what is the work done? And I can see it's all in joules, so that means I know the unit should be joules. So that's a little way for you to check if you forget the unit for something. They are written all over the questions. You can see them right here. All right. Now we're lifting something up. How much net work did gravity do? So what happens? It is lifted up and then comes back. Maybe I had plus 500 and then minus 500. It'll add up to 0. The net work is 0 if it returns to the original position. Work is only done once it moves. So a block is pushed over here with 3 forces. We need to find the net force on this block. The net work done, I should say. So that's basically W equals Fd. The net work done means I will just add and subtract all the forces. 15 and 10 going to the right, so that's 25 to the right. But I have 5 going to the left. So I will do 25 minus 5. 25 minus 5, that's 20. Multiply that by the distance of 3. 20 times 3 is 60. 2 times 3 is 6. Add a 0. 60. Nice. Over here, what is the work done pushing the cart 4 meters? So now if you have a graph, we already know W equals Fd, so force times distance. That just happens to be the area under the graph anyway. That's useful if the graph is like a triangle shape. If it's a triangle shape, then you'll do a half of the force times the distance, a half the base times the height. If we get to it, we can do it. This is easy. 4 times 30. I will do 4 times 30. You will get your answer. That will, of course, be 120. 4 times 30 is 120. Very nice. I'll write it 4 times 30. And there's 30, there's 4. Okay, next. And here we go. There it is, exactly what I predicted. We have this, and this is now a triangle. I want to know the work done, so I'll do a half of the base times the height. A half of the base times the height. That is the same as half force times distance. Force times distance, but only half of it. So that equals to a half times 3 times 45. A half times 3 times 45 will be 68. Very nice. There we go. C is the answer. All right. Identify the energy stored in the following things. Heat from a stove, warming a pot of water. Heat from a stove, well, that's just heat energy. Heat is a type of energy. We'll just call it thermal. Thermal is heat. Thermal energy is heat. Energy carried by electromagnetic waves. So electromagnetic waves such as light, that is simply radiant energy, radiation energy. Energy generated by moving electric charges. Electric charges as electricity. That's electrical energy. It's the same thing. Electricity is electrical energy. Electrical. Energy contained in fuels. Energy contained in fuels, that's burnt, so that's just chemical energy. Chemical is in fuels. Chemical. Energy stored in the nucleus of an atom, fission or fusion. Nucleus, nuclear, that's easy. Nucleus and nuclear. Nuclear energy. Nuclear energy. Energy stored in plants, which is for chemical processes. So photosynthesis is a chemical process, so we can say chemical energy. Chemical. There we go. Those are the types of energies. We have a few pages left. It's going to be conservation of energy. I'll make that in the next video. Thank you.